You see the sharing page? Already we are discussing in the last class. There is a range PRF, pulse repetition frequency, maximum non-ambiguous range, right? So now in this today's class, now I am going to repeat the same topics, and after that I am going to the radar range equation. Okay. First of all, already you know that range is nothing but a distance between the radar and the target is called radar, right? So if you want to find out the radar, so we know the how much of distance between the radar and the target, and uh, the signal will be signal having how much of speed. The speed we are going to represent it as c. That is the speed of light. And next, and how to calculate the distance? Here the distance is a two-way distance. Here we are taking it as a two-way distance. So that's why I are going to represent it as 2r. So the finally range, the normal range of the radar, we are going to calculate, that is r equal to ct, that is nothing but a time by product of speed into time by 2 is nothing but a distance. Next, pulse repetition frequency. This pulse repetition frequency is nothing but a number of pulses of sound produced in 1 second is called PRF. This pulse repetition frequency. Here, see here, this is the transmitted waveform and this one is the received wave. Okay, this is the pulse width. From this point to this point, this overall time period, you can call it as a pulse repetition time, right? So when you are transmitted the signal at this point, after some time period, it receives the one signal. That signal you can call it as a echo signal. Okay. So if the echo signal, this is nothing but echo signal, and this is also called as a echo signal. Okay. This echo signal is related to the, that means corresponding to the first pulse, and this echo signal is corresponds to the next second pulse. and this echo signal is corresponds to the third pulse, right? But what about these small echo pulses? This is also echo pulses. So if you get the received signal within the second pulse transmitted, that echo pulses is nothing but a disk. This is nothing but a, after transmitting the second pulse, we are getting the first transmitted echo signal. So this is nothing but a small one. So what is the difference between the large one and small one is, if you are getting the echo signal before going to the second pulse, the target is close to the radar system. That means the target is close to the radar system. In small one represented as when after some time period, it takes more time to receive the echo signal. So that means that is target is far away from the radar system. Okay. So that's why I represented a small received signal, sorry, large echo signal and a small echo signal. Okay, is clear? And next. So P represented as repetition time, repetition frequency, Fp equal to 1 by. We know that frequency is nothing but inverse of amplitude. Okay. This is the final definition of the pulse repetition time. Time between the beginning of one pulse and the second pulse. Time between the beginning of the one pulse and the start of the next pulse is called the pulse repetition time. Inverse of the time is nothing but a frequency. Very, very important definition. Next, unambiguous range. So already know the meaning of the ambiguity. Ambiguity is nothing but a little bit confusion. So why are getting the confusion here? So here we are transmitting one pulse here, and after some this overall from this point to this point, this duration we can call it as a pulse repetition time or pulse repetition frequency. Pulse repetition time or pulse repetition frequency, right? So within this pulse repetition time, we are getting the echo signal. There is no ambiguity. That means that echo signal is related to the first pulse. Suppose, let me assume after the duration of the pulse repetition time, that means first pulse transmitted, we are not getting any echo signal within this pulse repetition time. After some time duration, that means it takes more time to receive the echo signal. That time means after the one repetition time, that means if you are transmitting the second pulse, then we are getting the one echo signal. So now we are going to thinking about that. So that echo signal is related to the first one or second. There is some ambiguity is there. Okay, I understood. If you are transmitting the first pulse within the pulse repetition time period, if you are getting the echo signal, there is no confusion. That echo signal is related to the first transmitted pulse. Or the second point is, if you are transmitting the first pulse, but even though you are transmitting the second pulse, we are not getting any echo signal related corresponding to the first pulse. After transmitting the second pulse, we are getting some more echo signal. Here we are getting some ambiguity. That echo signal is related to the first pulse or second pulse. Okay. If the echo pulse is, that means the received waveform is, the amplitude of the waveform is high, that is related to the second pulse echo signal, and suppose that means that is nearer to the target is nearer to the radar system. Suppose the received echo signal is The amplitude of the received echo signal is very low. That means related to the first transmitted pulse. That means it is very far away from the target. Sorry, the target is very far away from the radar system. Okay, so that's why maximum unambiguous range. We are not getting any ambiguity without any confusion. We have to calculate the range. So before going to this, generally we can call it as a range is nothing but r equal to c into time by 2. C is nothing but the speed of light, T is the time of the signal and RAL, and 2 is nothing but a round trip around of the signal. But instead of time, you are represented as a PR. That is a pulse repetition time, or nothing but a pulse repetition frequency. 1 by T is nothing but a pulse repetition frequency. So C by 2 into PR. So this form of equation we can call it as unambiguous range. Okay. So duty cycle. So already know the formula of the duty cycle. T on by T on plus T off is nothing but a duty cycle. This is the T on period. The pulse width period is nothing but T on period. In this before going to the second pulse, the off condition can call it as a T off period. So the overall T on plus T off is nothing but a pulse repetition time. Are you understood? Okay. So T on is nothing but a pulse width. So we are represented pulse width here. So T on plus T off is nothing but this is nothing but T on period and this is nothing but T off period. T off period. So T on plus T off is nothing but a pulse repetition time. That's why here we are represented as PRT. Okay. So pulse width by PRT in terms of frequency, pulse width into PRT. Okay. Finally, can call this a average power by peak power. Average power by peak power is nothing but a Q. Next, minimum range. So now we are calculating the maximum range. What is the difference between the minimum range and the maximum range? Okay. We will get the minimum range of the target where we consume the time required for the echo signal. Echo signal to receive at radar after the signal being transmitted from the radar. That means if you are transmitted the signal, if you are transmitting the signal within the pulse width range, so then within the instantaneous time we are getting the echo signal. That range you can call it as a pulse minimum range. Okay, so it is called as a shortest range of the target. The R minimum equal to CT by. Next. Now the important topic is in this unit. One of the important topic is simple form of radar equation. That is one of the important topic, that is radar equation. So how can we calculate the radar? Up to now just we are calculating the range. That means there is a 2 points, in between the 2 points how much of distance we have. So how to calculate the distance? Here also we have to calculate the distance, but we have a lot of attributes here to consider, and we have to calculate the radar range equation. We have to consider the lot of attributes. Those attributes are nothing but a transmitted power, how much of power, how much of power we have to, by using the how much of power we have to transmit. Okay, at the transmitting section, we have to transmit a signal which at what at how much of power. Next, at the radar system, we are using some antenna here. There is a bistatical antenna or monostatic antenna. So bistatic antenna means we are using antennas for transmitting section and receiving section separately. Okay, monostatic means we are using duplexer here. For the both the transmitting purpose and receiving purpose, we are using only single antenna. Okay, so this is nothing but a antenna here. This is antenna gain. Depends upon the gain of the antenna and depends upon the free space propagation of the signal. And this is nothing but a RCS, radar cross section. RCS is represented as radar cross section. Okay, this is the transmitting section and this one is the receiving section. All of you listening? Understood? Up to now it is clear? Okay. So till now you are calculating some ranges, but the range you are taking is a simple range. That means how to take the distance and how to consider the target where it is. Now coming to the, if you calculate the radar range equation, we have to take some attributes. It depends upon the transmitted signal and the power of the transmitted signal. It depends upon the gain of the antenna, cross-sectional radar system, depends upon the free space propagation parameters. So all these by considering all these parameters, we have to calculate the radar equation. Okay, first of all, now this is nothing but a simple form of radar equation. That's, you can call it as a then you can call it as a standard radar standard standard form of radar range equation is also called as a simple form of radar range equation. Okay, we know that power density. So power density is nothing but a ratio of power and area, right? So power density is nothing but a ratio of power and area. So the power density we are representing as PDI. So all of you know down. Take your books and note down. It's very important topic. So I think we have to do it. So first of all, if we take the power density is nothing but the power and the ratio of the power and area. So the power density are going to represent PDI. So R from the radar can be mathematically represented as PDI equal to power ratio of power, that is transmitted power by area. Area is nothing but 4 pi R square. So PT is the amount of power transmitted by the radar transmitter. So this is nothing but 4 pi free space propagation, 4 pi R square. So this is the how much of power we have transmitted from the radar system. Power density is valid for isotropic antenna. Generally, in the radar systems, we are going to use isotropic antennas. Not only isotropic antennas, directional antennas, most probably we are preferable for the radar systems. Okay, directional antennas. Okay, so let us consider we are taking here isotropic antenna. In general, radars use directional antennas, therefore the power density, that is PD, here represented due to directional antenna will be PDD equal to PET represented as transmitted power. This is nothing the gain of the antenna by 4 pi r square. See the diagram. Transmitted power, gain of the antenna, free space propagation. Okay, product of transmitted power into gain of the antenna by 4 pi r square. Okay, right? So target radiates the power in different directions from the received input part. So the amount of power which is reflected back towards the radar depends on its cross section. So the power density PDE, that means E represented as echo signal. E represented as echo signal at radar can be mathematically represented as PDD. Okay, by PDD into sigma by 4 pi r square. So sigma is represented as a radar cross section. Again, once again, see the diagram here. PT G by 4 pi r square into radar cross section. PT G by 4 pi r square we can represent as PDD. Now the received echo signal, that means the PDA, power density of the echo signal is nothing but you are represented as PDE equal to PDD into radar cross section by 4 times. Okay, substitute equation 2 and 3. PD equal to, that is PDD is nothing but a, just write down the equations on your paper, everyone. So PT G by 4 pi r square into radar cross section by 4 pi. Okay, up to now it is clear? Any doubt? No. Up to now it is clear, everybody. Okay. Then the amount of power, that is the received power by the radar, depends upon the effective aperture area of the receiving end. Okay. So now up to now we are uh, considering the transmitted power, gain, free space propagation, radar section. Now coming to the receiving section of the radar. This is the aperture area of the radar. When we are receiving the signal, that signal will be how much of signal we are going to receive. It depends upon the cross-sectional area of the antenna, right? So now we are going to represent it as a, so the radar depends upon the effective aperture area of the receiving antenna. That effective aperture area we are going to represent it as A suffix E. That is the, from the receiving side, the antenna, how much of antenna aperture area we are going to represent as A. So now the received power equal to PDE into A. Already PD is nothing but a, this one. Okay. Received power is nothing but a PD into product of PD into A. So now substitute fourth equation and fifth equation. Already you know the PDE formula. That is this one. So PTG 4 pi r square into sigma by 4 pi r square into effective aperture. Okay. Now modify this equation. So PR equal to PTG sigma AU 4 pi by 4 pi whole square into R whole. So finally we are getting the R equal to PT transmitter power, gain of the antenna of transmitting section, radar cross section, effective aperture area of the receiving section, receiver side by 4 pi r square. That means free space propagation. PR is nothing the received power, right? Whole power 1 by this is nothing but generally range equation of the range. To modify the equation, Same, this PR can be modified up to, you can take the, from the PR, you can take the R value. So that is R is nothing but this. After modifying this Weber equation, we are getting R here. Understood? Give me your response quickly. Next, so the Weber equation, you can call this a standard form of radar equation. That means echo signal is having the power less than the power of the minimum detectable signal. Then radar cannot detect the target since it is beyond the maximum limit of the radar range. Okay. Generally, we are transmitting some signal. That signal having a high gain, uh, high power density. That given, which is the signal we are going to transmit it. The signal have high power and high density. But which is the signal we have received from the target, the signal having very less power, very less power. Because of that signal is nothing but an echo signal. When the signal is transmitted towards the target side, when it reaches the target, when it reaches the signal, touches the target, it resembles that. And the remaining, this is nothing but electromagnetic waves. So exact signal we are not getting. What is the signal we have to transmit it, that will not be received exactly. Why? Because we are, some part of the signal will be received, because of that signal is only the, when the signal touches the target, that signal, that's some part of the signal will be received. Okay, so due to that reflections, there is some losses out there. So that's why whenever we are receiving the echo signal, that signal having the powerless signal. Okay, the power of the minimum detectable signal. The radar cannot detect the target since it is beyond the maximum limit of the radar. Suppose, even though you are having the powerless, that power you can call it as a minimum detectable signal. Means, even though the power is very less, by using this power, we have to detect the target. Suppose we have to detect the targets, that power you can call it as a that signal you can call it as a minimum detectable signal. Okay. Suppose, let us assume radar cannot detect the target. If you are getting the some less power, by using that less power, you are not getting any signal or any target. That means it represents as beyond the maximum limit of the radar range. So now we are going to calculate where is maximum range, where is minimum detectable signal, and how to calculate the minimum detectable signal, and how can we calculate the maximum radar range equation. So that's why range of the equation we are represented as maximum radar range equation. How much of that means అసలు ఎంత లిమిట్ వరకు మ్యాక్సిమం మనం ఎక్కడి వరకు వెళ్తాం తేజస్విని. ఓకే, టెల్ మీ తేజస్వి, నిహారిక, తేజస్వి, టెల్ మీ. సో టార్గెట్ దగ్గర రేడార్ సిస్టమ్ నుంచి టార్గెట్ వరకు ఎంత డిస్టెన్స్ ఉంది అనేది మనం క్యాలిక్యులేట్ చేయాలి అంటే, మీరు ట్రాన్స్మిట్ చేసిన సిగ్నల్ అనేది రిసీవ్ అయిన దాన్ని బట్టి క్యాలిక్యులేట్ చేయాలి. సపోజ్ వెనెవర్ ద రిసీవ్డ్ సిగ్నల్ ఈస్ వెరీ లెస్. ఓకే, ఓకే అమ్మ. సపోజ్ యువర్ రిసీవ్డ్ సిగ్నల్ ఈస్ వెరీ లెస్, ఈవెన్ దో మీరు ఎంత పవర్తో ట్రాన్స్మిట్ చేసినా మనకి రిసీవ్ అయ్యే సిగ్నల్, దట్ ఈస్ ఎకో సిగ్నల్, దట్ ఈస్ ఎకో సిగ్నల్ హ్యావ్ వెరీ less power. So ఆ లెస్ పవర్తో కూడా మనం సిగ్నల్ టార్గెట్ని డిటెక్ట్ చేసాము అంటే యు ఆర్ కాల్డ్ యాజ్ మినిమం డిటెక్టబుల్ సిగ్నల్. ఎంతవరకు మనం రేంజ్ మ్యాక్సిమం రేంజ్ బియాండ్ దట్ లిమిట్ ఉంటే వీ కెన్ నాట్ క్యాలిక్యులేట్ ద డిస్టెన్స్ ఆర్ వీ కెన్ నాట్ ఫైండ్ అవుట్ ద టార్గెట్. సో మ్యాక్సిమం ఎంతవరకు ఉంటే it is supposed to be calculated. That so we'll get the following equations by substituting r equal to r maximum and pr equal to s minimum. Okay. Pr equal to okay. So r maximum equal to r maximum equal to ptg sigma a by 4 pi r square into s minimum. That's pr. This pr we are represented as s minimum. That means received power. That is a minimum detectable signal, which is the signal we have received from the target. That received signal we can call it as a minimum detectable signal. We are going to represent it as S minimum. Okay. So equation 7 represents standard form of radar range equation. By using the above equation, we can find the maximum range of the target. This is very important formula. Note down clearly. R maximum equal to PTG. This PTG sigma A by 4 pi whole square into S minimum. S minimum is nothing but a PR. Okay, whole power by 100. Okay, next. Coming to the limitations, there is some limitations in the standard form. That means simple form of radar equation. So that's why we are going to modified form of radar equation. Before going to this modified form of radar equation, first of all, what is the limitations of the simple form of radar equation? Okay, by using the simple form of radar equation, it is not adequate to perform the practical radar. That means by using simple form of radar equation, we have to calculate the radar range equation by theoretical only, not a practical purpose. Okay, so that's why we're going to modify it. Many important factors that affect range are not explicitly included. Many factors means maybe I think gain, power, radar cross section, aperture area. These are lot of attributes are there to consider to calculate the radar equation. In practice, the observed maximum radar ranges are usually much smaller than what would be predicted by the above equations. Sometimes as much as factor of 2. There are many reasons for the failure of radar. Simple radar equation could fail to actual performance. Actual performance means, so if you are taking all these attributes like transmitted power gain, radar cross section, antenna aperture, received antenna aperture area, received power, and phase propagation. All these depends upon all these parameters. By using this that means standard form of radar range equation. By theoretically only we have to discuss it. This much of range is there, this much of range is there. But practically it is not possible. So that's why we are going to modified form of radar equation. This is nothing but a modified form of radar equation. We know the following relation between the gain of direction antenna and effective aperture. So most probably, uh, whenever we are transmitting the signal will be transmitted towards the target side exactly. It depends upon the power and gain of the. Okay, so generally in the radar systems we are using the direction antennas. Okay, direction antennas means the direction antennas having very high beamwidth. Okay, so even though beamwidth is high, we are maintaining the high beamwidth. Okay, so sorry. beamwidth is less. The gain of the direction antenna is beamwidth is less. So less means the narrow beamwidth less ఉంది అంటే మనకి గెయిన్ అనేది చాలా హై ఉంటుందండి. సో టార్గెట్ని ఈజీగా ఏం చేస్తుంది. సో గెయిన్ ఈక్వల్ టు 4 pi AE by lambda. So now substitute this R maximum value. The above equation is R maximum equal to this one. So now substitute the gain value here in the R maximum. That's gain equal to 4 pi AE by lambda. Again, we have to modify the equation. We have to substitute the G value in the R maximum. Substitute the equation 7 in equation 6. So finally, we get the equation R maximum equal to PT sigma AE square 4 pi lambda square S min by power 1 by. This is the last step. From the equation 9 represents the modified form of radar range equation. So in previous section we are mentioning the gain. Now this section the aperture area is nothing but a gain into lambda square by 4. Okay. So already you know these type of values. All these formulas. I think ఇవన్నీ మీకు యాంటీనాస్లో వచ్చేసే ఉంటాయండి. అపర్చర్ ఏరియా ఫార్మ్ గెయిన్ ఇంటూ lambda square by 4. Okay. So now substitute this aperture area in this equation. So finally, the modified form of radar range equation R maximum equal to PT G square lambda square sigma by. PT is nothing but transmitted power, gain of the antenna, so wavelength of the signal. Next, radar cross section, 4 pi whole cube. S minimum is nothing but a received power, that means minimum detectable signal. For 1 wave. This last equation represented as modified form of radar. Okay. Tomorrow we will discuss the problems. Finally, this is the radar range equation. We have two types of radar range equation: simple form of radar range equation and modified form of radar range equation. Okay. This is the modified form. This is the simple form of radar range equation. At the side of the formula, we have to write it as this is a simple form of radar equation, and this is the modified form of radar equation. Okay, anybody have any doubts? Okay, today's class is over. If you have any doubts, ask me. Any doubts? Up to now it is clear.